Hello there and welcome back to this video series on control systems. Over the past few videos, we have been looking at topics on modeling and analysis tool with respect to finding the transfer function. We have seen block diagram reduction, and in the past 3 or 4 videos we have seen Mason's gain formula, and we saw that once the signal flow graph is drawn, finding TF is simply a matter of identifying loops and forward paths. We will go on to the one last topic that is left in Unit 1, that is classification scheme of control systems. After watching this video, you will perhaps be able to classify control systems and specify into which class a particular system falls. So I'll merely give the definitions and leave the task of solving problems to you as homework. In video 12, we have seen what we mean by a linear system and time invariant system. We will merely mention that once again in this video. With that said, let us see the classification scheme. Based on linearity, systems may be classed as linear and non-linear systems. Then based on inputs, the system may be classed as single input, single output system, or multiple input, multiple output system. Then based on continuity, continuous time or discrete time systems. Based on randomness, deterministic or stochastic systems. Based on open loop or closed loop, that is whether feedback exists or doesn't exist. Then time varying and time invariant systems, we have already seen this. Then causal and non-causal systems. We will try to present the definitions of these, and as we said, we are going to leave the task of working on problems for you. The first classification is based on linearity. If the system obeys laws of superposition, we have seen what law of superposition is. It is a linear system, otherwise it is a non-linear system. Most of the real life systems are non-linear very strictly. But in a small region around an equilibrium point, we may linearize them using calculus. In such case, we say the system is linear in that small region. The other classification we have seen is single input, single output, SISO, or multiple input, multiple output, which is quite straightforward. Then we have continuous time systems and discrete time systems. If the variables in the system are defined for every time instant, then the system is called continuous time system. Systems which are computer controlled generally have certain variables defined only at specific time instants, and we cannot say anything about what happens in between those time instants. If such is the case, we call the system to be discrete time system. Based on randomness, we can classify systems as deterministic or stochastic. A deterministic system is a system in which no randomness is involved in the development of the future states. That is, computing future states is a gunshot problem. Whereas in a stochastic system, there is a certain amount of randomness and probability distribution associated, and we may not be able to predict the output of the system precisely. Okay, we can only analyze them in a statistical sense. If such is the case, we call the system to be a stochastic system. One other important classification is causality. In a causal system, output appears only after the input. Output cannot appear before the input. If such is the case, we call the system to be a causal system. In a non-causal system, the output at an instant may depend on a future input, an input that is not yet applied onto the system. We may note that all physical systems are causal systems. One other classification is whether it's an open loop system or closed loop system. If there is feedback present, the system is called a closed loop system. If there is no feedback present, the system is strictly closed open loop system. If there is no feedback, it is open loop system. The next classification is on time invariance. I'll once again present what we have seen earlier when we are talking about LTI system. Let us say you have a system defined by this T with the relation y of t is operator T acting on x of t. Let us say you give some input, whatever is this x of t, and let us say we are getting some output. Okay, xt is the input, yt is the output, and they are related by operator t. Now to that system, same system, if you apply an input which is delayed by a time interval tau, you can see we just moved it to the right a little bit. If you do that and if you get the same output y of t delayed by the same time interval tau, such system is what we call time invariant system. We'll try to specify this a bit more clearly and with a mathematical notation. Let q sub tau be an operator that delays its input by a period tau. So q tau acting on any variable x or y or z will result in the same variable delayed by a period tau. Then the system denoted by operator t is invariant only if this equation is satisfied. That is, if you delay the input, the output is also delayed by the same time interval tau. With that, we come to the end of this video and we'll summarize that classification scheme of the control systems is presented. It may be noted that the course control systems we are studying focuses only on linear time invariant systems. I think that's all we have for now. Have a great day.